Every doctor gets a hospital, every hospital fills its slots, and nobody on either side wants to swap. Is that even possible? Dating apps, job markets, medical residency, they all share one shape. Two groups, and every member of each group ranks every member of the other best to worst. A matching pairs each person on one side with exactly one person on the other. The real question isn't whether you can pair everyone up, that's trivial. It's whether the pairing holds once people can see who else is out there. Will anyone want to break their match and pair up with someone else instead? That's the problem stable matching solves, and it shows up in more places than you'd expect. Hiring pipelines, school assignment systems, even national kidney donation registries, all running some version of the same underlying idea. Normally, side A and side B each write out a full preference list ranking every member of the other side, from favorite to least favorite. A matching assigns each person on side A to exactly one person on side B, using up every slot on both sides. That's the easy part, any random pairing satisfies it. The hard part is what happens after the pairing is announced, once everyone can compare their partner against every other option they could theoretically have got. If two people who aren't matched to each other would both rather switch to each other than stay put, the whole arrangement is in trouble, no matter how neatly it filled every slot on paper. Here's why this is harder than it looks. Say Alice is matched with Y and Bob is matched with X. Looks fine on paper, but Alice actually prefers X over Y and X actually prefers Alice over Bob. Both of them would rather ditch their current partner and pair up with each other. That's called a blocking pair, and it's the technical definition of failure here. A matching is unstable if any such pair exists anywhere in it. A matching is stable only when there are zero blocking pairs, meaning nobody anywhere has both the desire and the opportunity to defect. Randomly pairing people almost always leaves at least one blocking pair sitting there, quietly waiting to fall apart the moment anyone compares notes. 1962, David Gale and Gale-Shapley proved a stable matching always exists no matter what the preferences look like, and gave an algorithm that finds one. Every unmatched person on side A proposes to their favorite remaining option on side B. Each B compares the new offer against whoever it's currently holding, and keeps whichever proposer it prefers, rejecting the other. A rejected proposer crosses that name off their list and proposes to their next choice instead. This repeats propose, compare, reject, repeat, until every single person is matched. No coordinator, no central planner, just one simple local rule applied over and over until it can't be applied anymore. Let's trace 3 rounds with 3 people on each side. Round 1, Alice proposes to X, Bob proposes to Y, both get held. Kara also proposes to X, X compares Kara against Alice, prefers Alice and rejects Kara. Round 2, Kara, now free, proposes to her second choice Z, and Z holds her. Round 3, every single person is matched, nobody was rejected this round, so the algorithm halts right there. The final result, Alice with X, Bob with Y, Kara with Z. 3 proposals were rejected along the way, and not one lingering complaint survives anywhere in the final outcome. 2 things need proving, and both fall out of the same mechanism. First, termination. Every proposal permanently crosses one name off somebody's list, and there's only a fixed number of possible pairs total, so the algorithm can't loop forever, it runs out of moves. Second, stability. Suppose someone ends up wishing they got a different partner. They must have proposed to that person earlier and been rejected, which means that person was already holding someone they liked more, and from that point on they only ever trade up. So that preferred partner never wants them back either. No blocking pair can survive the process, which is exactly why the algorithm always lands on something stable. But stable doesn't mean fair to both sides equally. Whichever side does the proposing ends up with the best partner it could possibly get across every stable matching that exists for that set of preferences. That's called being proposer optimal. The side receiving proposals gets the opposite deal. The worst partner it could get across every stable matching, still stable, just the least favorable stable outcome available to it. Flip who proposes and you flip who benefits. The algorithm itself is neutral, but the setup you choose isn't. This is exactly why real-world matching systems fight hard over who gets to be the proposing side before the algorithm ever runs. This algorithm is already running parts of your life. National Resident Matching Program uses a stable matching process to place roughly 40,000 doctors into hospital residencies across the United States every single year. New York City and Boston assign students to public schools with variants of the same idea. Kidney exchange programs use related stable matching logic to chain together incompatible donor-recipient pairs into working swaps. Some labor markets and academic hiring clearinghouses lean on it too. One deceptively simple propose and reject loop published over 60 years ago, still quietly clearing real high-stakes markets today. Thanks for watching.